Welcome to the another video on VLSI design. Before we move on to the today's video, let us try to recapitulate what we have discussed in the previous video. We have discussed MOS transistor theory, followed by the transistor symbolic representation, and we mentioned there are three different or variety of NMOS and PMOS representations. The first one is going to be circuit schematics, and the second is going to be the detailed representation of the NMOS and PMOS transistor symbols. And the last column we have discussed a not commonly used transistor symbols. Following this, we have discussed even the majority charge carriers in the NMOS and PMOS transistors. The majority charge carrier in NMOS transistors are the electrons, whereas in PMOS transistor, the majority charge carriers are the holes. And later we have discussed the demonstration of the MOS structure. In this demonstration, we have isolated the MOS structure that consists of only the gate and the body, and without the source and drain regions. And in this context, we have explained three modes of operation. The first mode is going to be the accumulation mode. So here, as you can see, the MOSFET, we have shown the three layers without including the source and the drain region. The three layers are namely polysilicon gate, which is the top layer, and the middle we have a thin silicon dioxide insulating layer, and the bottom we have p-type body layer. So these three layers forms a capacitor, a parallel plate capacitor, which is shown here, which is the silicon dioxide acting like an insulator separating the two layers, which is namely the polysilicon gate and the p-type body. Now we have to demonstrate the MOS structure. The first mode is going to be the accumulation mode. For the accumulation mode, we apply gate voltage which is less than 0, which is typically a negative voltage. When the negative voltage is applied to the upper plate, okay, the negative charges, as we can see here, this induces the positive charges. The positive charges are accumulated in the body region due to the capacitance effect, and this mode of operation is called as accumulation mode. As we can see, too many positive charges have been accumulated beneath of silicon dioxide. The next mode of operation is going to be the depletion mode. To explain the depletion mode of operation, we apply the voltage, gate voltage, greater than 0 volts but less than the threshold voltage. Typically threshold voltage is considered as 1 volt. When we apply voltage within this range between 0 and 1 volt, so here the positive charges now in the upper plate, because we apply here positive voltage, therefore the polysilicon gate has now positive charges has been provided to the upper plate, and below we can see some changes that has happened here. Because of upper plate as positive charges, that repels the holes present in the body region. So the holes have been pushed away from the beneath of silicon dioxide. So that creates a layer or region called as a depletion region. Okay, and here in this depletion region, the condition required is going to be the gate voltage should be very small. Okay, so when we increase the gate voltage, what is going to happen, that is discussed in the next mode of operation, which is called as inversion mode or inversion layer. It's going to be formed here. So what do you mean by that? Again, here the gate voltage is large, which is far greater than the threshold voltage, which is 1 volt. Say for example 3 volts is applied. So large gate voltage, positive gate voltage applied to the polysilicon plate. Now we can see the changes happened beneath of silicon dioxide or in the body region. So the positive voltage upper plate attracts the negative charges, which is they are the minority carriers in the p-type body, and those minority carriers are attracted below the silicon dioxide layer, and this forms the inversion layer. The reason why it is called an inversion layer is because the complete body was a p-type, and the voltage applied to the gate has now converted this p-type body, a region here below the silicon dioxide, which is of p-type body. It has converted to the n-type, therefore, and this layer is called as an inversion layer, and conversion from p-type to n-type, that is has changed. Okay, the region is called the inversion layer. and below that you can see that again there is a gap here. That is because of the positive charges are still pushed away, and that forms a depletion region here. So this mode of operation is called as an inversion mode or inversion layer formation. The inversion layer itself is called as a channel. Now this channel acts like a path for the charge carriers to move from source region to the drain region. That is explained in the operation of the MOSFET here. So this is the theory that we have covered with reference to the MOSFET. And let us look into the today's topic. Today's topic we are going to discuss on the operation of the NMOS transistor. Here we pay attention to the NMOS transistor, so that working of PMOS transistor can be understood once we explain the working principle of the NMOS transistor. As we know, the structure of the NMOS transistor is a MOS stack. So it is made up of metal as the top layer, followed by there is an oxide layer in between, and there is a silicon layer, okay, which is the body layer. So this forms a stack of 3 layers, okay, between the two type of regions, namely the source and as well as the drain regions. Okay, so this is the structure of the MOSFET. And now let us try to understand the working principle of NMOS enhancement transistor. This is an enhancement transistor, and here we have different modes of operation. First, let us consider the cutoff mode. Okay, to operate NMOS enhancement transistor in cutoff mode, there are certain conditions to be fulfilled. The first thing is the gate to source voltage, which we call as VGS. That should be less than the threshold voltage. Threshold voltage is labeled as VT. When we apply gate source voltage VGS, okay, so let us call this as a VGS, is less than the threshold voltage. Threshold voltage is typical value is going to be 1 volt. When gate to source voltage is less than 1 volt, and we don't apply any drain source voltage here, so drain source voltage is taken as 0, applied is going to be 0, and this turns off the transistor. Transistor is not turned off, and it is turned off, transistor is turned off, therefore the drain to source current is going to be 0, and that is explained through this structure here. As we can see that VGS is made as 0 here, gate to source voltage, okay, and VGD, last class we explained the relationship between VDS, VGS and VGD. So the relationship is the VDS equals, this is what we have derived in the last class, VDS equals VGS minus VGD. This was the relation that we have shown in the derived in the last class, and VGD is also going to be 0 because of VGS. Both are going to be equal, and this makes the these two regions, N plus regions and this source region, as isolated, because in between there is a body region here, and so these two regions will not, the charge carriers from these two regions cannot move. So therefore the current drain to source current is going to be 0. So we can conclude from this, there is no channel formation in the cutoff mode, and the drain to source current is going to be 0. To arrive this cutoff mode, the condition required is the gate to source voltage must be less than the threshold voltage. And the voltage applied within this, okay, makes the complete transistor as off. Okay, the transistor is not conducting. Okay. And next, let us see the few points under this mode of operation. The source to drain contains free electrons. As we can see, they have free electrons, while the p-type body also has got free holes, as we can see here. But here the electrons from here, they can't move to the drain region here, because these two regions are isolated from each other, so they are not connected here. If the source is grounded, okay, the junctions between the body and the source or drain are either zero biased or reverse biased. What do you mean by that? Here we can just interpret like a diode or PN junction. Okay, as we can see here, we can also consider this like a PN junction, and look at the bias conditions for this PN junction. So this the cathode of this is at 0 volts, and anode is also at 0 volts. So we can say that is a zero biased or reverse biased. So therefore again, this diodes in the peripheral of this N plus region of source and drain, they are zero biased or reverse biased, they will not allow the current to flow through the body region here. So therefore, the drain to source current is going to be zero. And this shuts off the transistor. Transistor is considered as it is in the off state, and the cutoff mode is henceforth it is defined. Okay. Let us see, when the transistor is in the off state, is typically approximated as zero. That means there is no current flow through the transistor. There may be some leakage currents, that exist in the transistor, but that is very small and that can be neglected. But when the millions and billions of transistors are there in today's chip design, we won't design a few transistors, but instead we go for millions and billions of transistors we accommodate in a single chip. And leakage current of each one of these transistors may become a substantial value, and that need to be considered when we go for a millions and billions of transistors. The current through the off transistor is also to be taken as a serious issue, because when the huge number of transistors are designed in today's the complexity. And let's move on to the second state of operation. As we have seen, cutoff mode, when we apply this condition VGS less than VT, so transistor remains in the half state here, and we are not applied even VDS also, and therefore the current flowing from drain to source is zero, or charge movement from source to drain is going to be zero. The transistor remains in the half state. Let's move to the next one, where we turn on the transistor, but there exists a formation of a channel, but current cannot flow from drain to source. That's going to be considered in this case. So let us see how this can be illustrated. Here the gate voltage is greater than the threshold voltage. That's the first condition. We want to turn on the transistor, therefore we apply gate to source voltage which is greater than the threshold voltage, which is typically a 1 volt. Okay. So we are expecting here the gate to source voltage to be applied more than threshold voltage. Let's say, for example, we are going to apply 5 volts as the gate to source voltage. And look at here now, the drain to source voltage in this case is not applied. So VDS is going to be 0. So I'll write it here, all voltages that we apply here. So VDS is not applied for this. So VDS is going to be 0. When VDS is going to be 0, then VGS becomes equal to VGD. How do you arrive this one? Again, we can go back to the equation that we have derived. We have it is VDS. So which is VDS equals VGS minus VGD. So when VDS equals to 0, this is going to be 0. Therefore, VGS becomes equals VGD. Okay. So the voltage applied here between the gate and source, this voltage becomes equal to this voltage. Okay, VGD. What happens inside the body? Let us see here for the voltage that is applied. When VGS is greater than VT, that means the gate is provided with the positive type of charges. A positive voltage is applied to the gate, and look at the changes happened in the body region, and we have seen this in the inversion layer has been formed here because of large voltage that is applied to the gate, and holes have been pushed downwards. As you can see here, holes have been pushed downwards in the body, and there is a depletion layer, and as well as there is a inversion layer. As you can see, there is here we have an N-type inversion layer has been formed here, and now this creates a path for the charge carriers from source region to the drain region. So charge carriers can move from source to drain like this when we apply some drain source voltage, but here we have not applied any drain source voltage, so therefore the current flow through this is going to be 0 in this case. So even though we apply gate to source voltage beyond the threshold, say here we have taken 5 volts, but VDS is equal to 0. But here VGS greater than VT, this induces a channel here. So here we can say that for this particular condition, channel formation, channel exists, channel induces. induces in the p-type body. Channel has been induced in the p-type body, but still IDS is going to be 0 because the VDS is not applied here. Okay, so VDS is going to be 0. So VDS is required for the current to flow from drain to source or charge carrier to move from source to drain. That we'll see in the next mode of operation. But here we just simply turned on the transistor and the channel has been formed here. So there is no current flow from drain to source. Let's go through the points here. The gate to source voltage is greater than the threshold voltage that turns on the transistor. A conductive inversion layer of electrons, majority charge carriers, forms between the source and drain. We have seen that there is a formation of N-type channel between the source and the drain region. As the gate voltage increases, as we increase the VGS here from 5 to say 6 or 6 to 7 or 7 to 8 like this, what will happen? So the number of charge carriers, a number of carriers in the channel increases. So here N-type charge carriers, the strength or the quantity of this N-type charge carriers keeps increases. So here I can say that Q keeps on increases. Electrons keeps on Q and keeps increases because of increase in the voltage. So that increases the conductivity. So conductivity of the channel keeps increases, but still current is not flowing because of VDS is going to be 0. Okay. Next, let us see here. So in this case, as we said already, the drain to source voltage, this is a relationship we have derived in the previous video. The potential difference between the drain and source is given by this VDS equals VGS minus VGD. And if VDS is going to be 0, then VGS is equal to VGD. There is no electric field present to drive the current from drain to source. So that means the current flow from drain to source is going to be 0. So this shows that IDS equals 0. This is the second level of operation. In the third mode, we will see that. Okay, here also we will already in the second mode we have seen that channel has been formed, but there is no current flow. But here current flow exists, and this is the third level of operation, which is called as a linear mode or triode region of operation, and that is the figure required, diagram required is shown here. Let us see how this conducts. First of all, the VGS should be greater than VT. This induces the channel. So let me write it here. VGS should be greater than VT. VT we already taken a value as typical value as 1 volt. We can apply any voltage greater than 1 volt. Of course, let us say here we are going to apply say 5 volts as VGS, and that is beyond 1 volt. Definitely the channel formation takes place here. So this shows that channel has been induced in the body or p-type body, induced in the p-type body. So we can see here channel already it has been induced. N-type of channel has been induced in the p-type of body because the gate is provided with the voltage, positive voltage, and it is very large voltage. VGS is greater than VT. And now let us see whether this creates the current flow from drain to source or not. But now instead of making VDS as 0, we apply the VDS now. And what should be the magnitude of VDS? This is what the proportion we apply the drain source voltage. VDS is now drain to source voltage. The voltage applied here, this is going to be the drain terminal, and we have a source, and here we have a gate. Okay, so between the drain and source, VDS, that should be greater than 0, but it's less than VGS minus VT. That means we apply here small drain source voltage. Okay. VDS is not large, but it's small drain source voltage. So what will happen here? So obviously the channel, earlier we have seen that there was a uniform channel from source side to the drain side. But now, as we can see from this diagram, channel is not uniform. we can see channel depth is high on the source side, whereas channel depth is less on the drain side here. Why this happens, we'll explain that in a minute. So here the voltage at the source side, the influence of VGS is high, whereas here at the drain side, the VGD decides the depth of the channel. Okay, so we have to relate now VDS to VGD so that we can easily understand why there is a tapered shape of a channel at the drain side, and or else in other way, why there is a channel depth is high on the source side and depth is less on the drain side. So to explain that, so we'll take up a expression that we have shown in the previous video. So this is what the expression we have shown. So VDS equals VGS minus VGD. Let's take for example here, we applied here 5 volts here, and VDS, let us say we have applied, VDS must be the VGS minus VT. Let us calculate what is VGS minus VT. So VGS is 5 volts, VGS minus VT becomes 4 volts. Okay, so the VDS must be in between 0 volts and 4 volts. So we have a 0 volts here, VGS minus VT we have calculated here, that is going to be the 4 volts. So it must be less than that. Let's say that we have applied the VDS as say 3 volt. Okay, we can start even from 0 and see that what is its effect on the VGD. Let's apply, I can't apply 0 because that must be greater than 0. I must apply the drain source voltage beyond greater than 0. Let us start with 1 volt as VDS. Of course, 1 volt lies between 0 and 4, therefore 1 volt can be applied. So now let us see what is the VGD. So VGD is nothing but, having known the VDS, which is 1 volt here, VGS is 5 volt. So obviously the VGD will be the 4 volts. VGD will be the 4 volts. So you can see here there is a difference in the voltage. This side, as I mentioned, the VGD is responsible for the channel depth, whereas here VGS is responsible for the channel depth. So 5 volts exist here. The voltage drop in the channel is not uniform now. 5 volt is the drop at the source side, whereas 4 volts is going to be the drop at the drain side. This is the VGD will decide the voltage drop at the drain side. This is when we apply VDS as 1 volt. Suppose if we increase VDS from 1 to 2, now let us see what happens here. When VDS is increased from 1 to 2, definitely there will be a decrease in the VGD. So what will happen to the VGD now? So VGD is now, this is VDS applied is now it's going to be 2 volts. VDS is 2 volts. So VGD becomes now, VGD is not now 4, it becomes 3. Okay, 3 volts. That means here on the source side 5 volts exist, but the moment again if I consider as 2 volts, still this 2 volts lies within this range. So therefore this as increase in the VDS from 1 to 2, the VGD has been decreased from 4 to 3 volts. Let us now replace here 3 volts. So that means again here one side there is a 5 volts voltage drop, on other side there is a 3 volt. Slowly there is a, we can observe there is a pinch off is happening, and if we go from 2 to 3, this drops from 3 to 2, the VGD voltage drops from 3 to 2. Still there is a scope for movement of charge carriers because 5 volts here and but 2 volts here. This region is not completely closed. Okay, it's not pinched off. And the moment if I go for VDS as 4 volts, and what will happen to the VGD? VGD becomes 1 volt. Now we can see here VGD is now 1 volt here. So now it's almost reached a threshold at on the drain side, but on the source side there is a 5 volts here. There is a channel depth is high, but whereas here it's already reached a pinch off, which is 1 volt. And beyond this, if we increase, this region is going to get saturated, and that's discussed in the next mode of operation. But here in the linear mode, as we can see here, so we have varied VDS all the way from 1, 2, 3, 4. This VDS has been increased from 1 volt, 2 volt, 3, and 4 volts. So in all these things, when the VDS is increased, corresponding drain to source voltage also increases. IDS also increases. Okay, and so therefore the current in this is going to be behave in a linear manner. That's why the name is linear mode. So now here current depends on the both VDS and as well as VGS. Even increasing VGS also increases drain source current. Increasing VDS also increases drain source current. But at some point, if we keep VGS as a constant and increase only VDS alone, at some point the pinch off will start, and charge carrier movement from source to drain will get saturated. Okay, so this mode of operation till the pinch off from all the way from 1 to 4 is called as linear region here. Okay, so that is the mode of operation, linear region mode of operation here. And now let's move to the next one, which is the saturation mode. What happens when the voltage VDS is beyond this VGS minus VT? Then the charge movement from source to drain gets saturated, and current flow from the drain to source becomes almost a constant. So let us see that in the saturation mode. In the saturation mode, if VDS becomes large enough, okay, so when VDS is large, then VGD becomes less than VT. As we can see from this equation, VDS is very large, so then VGD becomes less than the VT. So when VGD becomes less than VT, we already seen this here, VGD already reached VT, but further increase in the drain source voltage, that makes VGD here voltage less than the threshold voltage. So less than the threshold voltage, and that is the condition for saturation. That means we say that when VGD is less than the threshold voltage, which is 1 volt, less than 1 volt, we say that transistor is moved to the saturation region. So channel near the drain is no longer inverted, okay, and becomes it's a pinched off. Okay, so that we can see the next diagram. So we can see here channel has been pinched off. Okay, pinching means it's already almost it is a block. There was only the constant movement of charge carriers from the source to drain. Despite this, current conduction continues due to the drift of electrons under the influence of positive drain voltage. So here there is a drift of electrons, even though the channel is completely saturated. On the drain side here, it's something like this. The channel gets saturated here. So there is a drift of electrons movement from the source to drain because of the drain source voltage that we applied. And VGD in this case for saturation, it will be less than VT, and VGS will be greater than VT. This forms a channel, and this VGD less than VT pinches the channel on the drain side because it becomes less than the threshold voltage. So the electrons reaching the end of the channel are injected into the depletion region near the drain. As we can see, channel has been completely saturated and are accelerated to the drain terminal here. They are injected into the drain terminal here. In this mode, the current drain to source current is controlled only by the gate source voltage, because increase in drain source voltage beyond this point, VGS minus VT, now doesn't have a control on the drain source current. So IDS becomes now it is a function of VGS alone. Okay, IDS is now it is completely independent of VDS. That means any increase or decrease in the VGS that can change the drain source current, But VDS, any variations in the VDS, that doesn't have any impact on the drain source current here. Okay, so VDS doesn't no longer influenced by the drain source voltage. That is what it is clear in this one. So in this mode, what we have observed here is a channel has been pinched off, and IDS now is independent of drain source voltage. Okay, that is the fourth mode of operation. All these diagrams has been now summarized here. What we have seen in the first level, we have seen that no channel formation, drain to source current is 0. That's because of gate source voltage is 0. VGD is also 0. VDS is also 0. In this mode, VGS is 0. VGD is also 0. VDS is 0. No current flows. Therefore, IDS is equals to 0. What about here? In the second level, we have taken VGS greater than VT. As you can see, there is a channel formation. Here, no channel, but there is a formation of a channel. But channel is uniform because we applied VGS greater than VT and VDS is equal to 0. So here VGS is greater than VT, VDS is 0, and VGD equals VGS. So what we can observe is channel is uniform. So we can say here there is a uniform channel formation between source and drain. Source and drain. Okay, the channel is not pinched off in this case. Now let us see the third case. VGS is greater than VT. This forms a channel. Now VDS is now less than VGS minus VT. And this mode is called as linear mode. Here channel is formed, VGS greater than VT. This forms channel formed. Okay, as you can see, a channel has been formed. But now influence of VDS will be there because we are applying 2 voltage across the channel. And to observe the effect of this pinch off, we need to take here voltage at the source end will be the voltage at source will be VGS, whereas voltage at drain will be VGD. So we should see the values of these voltages to understand the tapered shape of channel in the linear region. So the VGS and the VGD decides decides the type of the channel formed here. As you can see, channel is like tapered shape like this. Okay, but VDS is of course very small, and therefore here IDS exists. The current now IDS in the linear region is now function of both VGS and VDS. That means variation of any one of this will change the drain to source current. Okay, and this mode of operation is called as linear mode. Lastly, we have a saturation mode. In saturation mode, we have VGS greater than VT, that forms a channel. This is channel is formed or induced, but VDS now is very large, but here VGD will be less than VT. VGD will be less than VT, whereas here, unlike right here, for this particular in the linear region, VGD is greater than VT. The voltage here is greater than VT but not less than VT. So we didn't see any here. We didn't see any saturation here, but there's a pinch off exists. Okay, because VDS applied is small. But here, channel is now the current flow is going to be linear because it's a function of both VGS and VDS. Whereas here, drain to source current in case of saturation region is a function of VGS, but IDS now is not a function of VDS. It is not a function of VDS. Okay, so it flows only under the influence of VGS. So this voltage that we apply here doesn't have impact on the current flow from drain to source, because current becomes almost like a constant, and any increase in VGS will increase the drain to source current. And this mode of operation is called as saturation mode. In saturation mode, channel has been pinched off, IDS becomes independent of VDS. Now let us summarize the transistor operation. The NMOS transistor has three modes of operation. The first mode is cutoff mode. VGS less than VT, transistor is off, drain to source current is going to be 0. The second mode is linear mode or triode mode. For this mode, the gate to source voltage should be greater than threshold voltage, but drain to source voltage applied is small. The transistor behaves as a linear resistor in this mode, and current flow is proportional to both VGS and VDS. Both the IDS is a function of VGS and VDS. In saturation mode, gate to source voltage is greater than threshold voltage, and drain to source voltage applied is very large. When VDS is very large, the drain to source current becomes independent of VDS. The transistor acts like a current source in this mode, and it's independent of VDS, of course, and is controlled only by the VGS. And if you look at applications of a transistor in the cutoff mode, transistor it acts like a half switch, whereas in the linear mode, transistor act like a on switch. And in the saturation mode, we can use transistor for amplifier application. So for transistor to work as an amplifier, we should operate in the saturation mode. It behaves like a constant current source. So these are the three, two different applications, not three. This belongs to almost all our computers works in this switch off mode or in the on switch, as an on switch or off switch. Transistor at a very high speed, it switches from off to on to off. So generally this happens in a computer. Whereas if you want to use MOSFET or NMOS or PMOS as an amplifier, so we must operate in the saturation mode. And so far we have discussed the transistor operation considering NMOS transistor. But now if you look at PMOS transistor, the operation of a PMOS transistor is exactly same as NMOS transistor, but it operates in the opposite manner, but the voltages and currents are going to be negative. Okay, so the n-type body is tied to the high potential in this case, high voltage in this case. So the p-type source and drain are normally they are reverse biased in this case. When we apply gate with high potential, there will be no current flow from the drain to source here. Okay, we'll go through the structure, we'll understand better. When the gate voltage is lower, so when we apply here a lower gate voltage, which is less than the threshold voltage, holes are attracted to form a p-type channel, as we can see here. So we are applying a negative gate voltage here, and look at the type of body here. It's the n-type body here, and the majority charge carriers in this are the electrons, and minority charge carriers are the holes. And the holes will form a channel here, and here the channel is now inverted because n-type body below the silicon dioxide, it has converted into the positive charges. It's made up of p-type holes. This forms a channel. This forms a channel connecting the source and the drain. So p channel beneath the gate, enabling the current flow between the drain and source. So here majority charge carriers are the current flow is due to the holes. So therefore the p channel is been formed here. This is a p channel. P-type channel has been induced here. The threshold voltages of NMOS and PMOS transistor are not necessarily equal. Generally, the NMOS transistor we have taken as plus 1 volt, whereas for PMOS transistor we will take it as a minus 1 volt. That is the threshold voltage. And the graph of this VGS versus ID graph, if you take VGS along the negative of x-axis and ID along the negative third quadrant, negative. Both are negative for the PMOS transistor. The graph for the PMOS enhancement transistor looks like this. So we have here a VTP, which is a typical value is going to be -1. More negative we apply, then more large current flows in the transistor, as we can see here. Okay, so VTP, this is called VTP, is negative for the PMOS transistor. Okay, that's the PMOS. Okay, and now let us see the symmetry and carrier flow with reference to the transistors. MOS transistors are symmetrical devices. As we can see, source and drains can be interchanged. But by convention, majority carriers flow from source to drain. Okay, that we already demonstrated with reference to the NMOS transistor. NMOS transistors, electrons are the majority charge carriers, and they flow from the source to the drain, and current flows from drain to source. Whereas in case of a PMOS transistor, holes are positively charged and they are the majority charge carriers, and they flow from source to drain with reference to the PMOS transistor. In a static CMOS gates, the source terminal is close to the supply rail, so while the drain is very closer to the output here. Okay, so we've already seen CMOS logic design, how to make a variety of gates using CMOS, and we have already shown that a drain is close to the output. Okay, so next one is the ideal current and voltage model of a transistor. Many times we need to develop a model of a transistors in order to use them in the variety of the CAD tools. An ideal current voltage model is developed that relates the current and voltage in the MOS transistor. Okay, that model is called as ideal IV model, and the delay in the MOS circuits depends on the time required for the capacitor, the current to charge or discharge the capacitor, because how much time, because the entire logic gates operate in the form of a charging discharging. Okay, so the delay of the MOS circuits is measured based on the time taken to charge and discharge the capacitors. So transistor capacitors mainly are of different types here, but we deal with only the main capacitors like gate capacitance. That gate capacitance is crucial as it attracts carriers to the channel, and this enables the device operation. We have already seen in the different modes of operation how exactly gate capacitance plays a vital role in the MOS transistor operations. So additionally, there are other capacitors, namely the parasitic capacitance that arise in the PN junctions between the source or drain to the body. These capacitors are called as a parasitic capacitance. Of course, they also have an influence on the MOS delay, MOS delay, because this influences the total delay in the MOS circuits. Of course, the parasitic capacitors. Another type of capacitance that we come across is going to be the interconnect capacitance. Interconnects are nothing but the wire capacitance of the wires connecting the different transistor is also significant. The wire can be modeled as a RC element like this, and there are infinitesimally many RC elements, such RC elements in the wire. We can model the entire wire with many RC sections like this, resistance and capacitance. And this capacitance need to be charged and discharged so that the current can flow through the wire. So this capacitance also creates a delay between the one transistor to another transistors. Okay, and these are the things which have been included in the ideal IV model. But let us see the limitations of idealized IV model. Though this provides qualitative understanding but lacks in quantitative accuracy, especially for the short channel transistors. That is the first limitation of idealized IV model. And the second thing is the spice based models, which example for that is a BC model, which offer a thorough representation of the MOS transistor, but requires extensive knowledge to use it as an effective way. Okay, and other simulations like spice simulations SPICE stands for Simulation Program for Integrated Circuit Emphasis. Very popular, a tool to simulate the transistor that provide detailed insights into the digital circuit behavior. Okay, SPICE simulations. So that's something with reference to the idealized IB model. Okay. And simplified performance of estimation models are nothing but the ideal IB model is still too complex for quick calculations, especially threshold voltage calculations, current calculations. It is still complex. But simpler models are also introduced to estimate circuit performance effectively. Okay. And looking into the DC characteristics, transfer characteristics, what we call to draw for the CMOS gates, specifically for inverter, IV models are applied to analyze the DC transfer characteristics of CMOS gates and even the PAS transistors. And this understanding is very important for designing the MOS circuits and even optimize the MOS circuits. Okay. So with that, we have come to an end of this video. In the next video, we will derive the equation for the drain to source current in the different regions, especially the cutoff region, linear region, and saturation region. We'll show that what is the magnitude of current flowing in each one of these regions. So with that, we'll end up this video. Thank you all for watching this.